Sorry about that. Something was wrong with my computer there for a second. Okay, so we're going to talk about conditional probabilities today. There's several different ways that these might be presented. The first one we're going to work with is called a contingency table. And sometimes they're called a two-way frequency table, but technically they can have like 3, 4, 5, 6 categories. This one just has 2. So it's going to relate to different categories, basically. Now, I'm just going to make kind of like a little mark on mine, really. Not all the tables will have all this information if you're presented with this, like on a Math Excel or a worksheet or something. Sometimes they just do the core information, which would be those 4 numbers I kind of just put brackets on. Sometimes they don't do the row and the column that have the totals. So let me just kind of show you how this works just real quick. So basically you have 2 categories in each direction. So male or female, and then right-handed or left-handed. So across the top row, this is just representing guys. The second row is representing girls. The first column is representing right-handed, and the second column is left-handed. The third row across the bottom is just adding the totals for right-handed or left-handed. So like down here, 43 and 44 is 87. 9 and 4 is 13. Okay, on this side, the totals here in the third column add across the row. So there's 43 guys that are right-handed, 9 that are left-handed, 52 total. So that's what's going on in those. And then the bottom corner, this is the total here across the row, total here across the column. This should be the same number. So 52 and 48 is 100, 87 and 13 is 100. Those should be the same number. If they're not, then there's something wrong with the data in the table. Okay, so just know there's no probability here at all. Just can you guys read the table to me? How many people are represented in this survey? And it's a number in the table. How many total people are they analyzing here? 100. It's just going to be this bottom corner here. All right. How many people in this table are female? 48. Okay. How many are male? 52. Okay, you guys understand. Do what? Was that English? What? Oh, okay. Well, they answered that way on the survey. We're not trying to misgender anybody. Okay. What about how many people in the table are right-handed? 87. How many people in the table are left-handed? 13. Okay, so you guys get this. Now, we're going to calculate some probabilities from this table. We've done these types of probabilities before. So what's the probability I randomly pick somebody that's been surveyed here out of this table and they're right-handed? Right, okay, so out of the whole table, 87 people, it doesn't say anything about whether they're a guy or girl, it just says 87 total right-handed, so out of 100. And then if you guys want to write that, it's 87% or 0.87 as a decimal, those are all okay. What would you tell me if I asked you, what's the probability I randomly pick somebody from this table and they are female? 40, I know this is tricky, so this is 48 out of 100. We're going to do that literally like the bottom example. It's called a conditional probability. That's what we're going to do today. These are just really general probabilities here. What is the probability I am male and so good, 43, male and right-handed. So that would just be this box right here, the male right-handed. So this would be 43 out of 100. What's the probability I'm female and left-handed? 4 out of 100. Good. Okay, now these are a little weird because these last two, these are not mutually exclusive. So there is an overlap here. So whenever you have an or statement, there can be some overlap, and let me pull this down so I can actually see the table here. When I do this, you got to think about it for a second because we might count something twice. So this says male or left-handed. So just in general, probability I randomly select a guy from this table would be 43 out of 100. If you guys remember the or statements for probability, you're going to add the probabilities together. The probability I am left-handed, just in general from this table, is going to be what? 13 out of 100. Okay, now I can just add those, right? Because they have a common denominator. I don't have to worry about that. But did I count anything twice? The 9. Okay, that's what I was going to say. So there's an overlap here. So basically when I counted, oh, I just wrote the wrong, idiot, sorry. This should have been 52. I'm sorry. There's 52 males. I don't know what I was doing. I did right-handed males. It's totally fired there. Okay, 52 should have been on the top of that first fraction. I'm sorry. There's 52 guys. Okay, 52. And then, so when I do that, I'm counting the 9 here. And then when I count left-handed, I count the 9 again. So you actually have to subtract off the overlap, which would be the 9 I counted twice there. All right, so then we're just going to, we just have a common denominator. So we're just going to do 53 plus 13 minus 9. So this should be 56 out of 100. So if they're not mutually exclusive, that can happen when you have an or statement. You have to subtract off the overlap. So female or right-handed. So probability I'm female, I'll make sure I grab the right number here. Probability I'm female, there's 48 in this survey out of 100. Right-handed, there's 87 out of 100. And then if I look at that, when I'm counting the females, I do the 44 and the 4. When I do the right-handed, I do the 43 and the 44. I counted that 44 twice. Remember, your probability cannot be more than 1. So if I had just done the 48 and the 87, that would have been more than 100 over 100, which would have been more than 1. So not possible. That means that you've got events that are not mutually exclusive. So they have an overlap here. So we got to subtract that. So this should end up giving you 91 over 100. Yes, you just, because you counted them twice. That's exactly the formula from yesterday. Go ahead. You forgot. Okay, now. All right, now, this is, I'm going to use this same table for the problems at the bottom here, but we're going to talk about a conditional probability, and we have not done that yet. So, conditional probability here. When you have a conditional probability, you're going to have two events. They're going to call them A and B the way this is laid out. And it says the probability that an event B will occur given that another event A has already happened. Okay, so we're not assuming it has happened, okay? And this can also only exist when you have two events that are dependent. So if you have a conditional probability, the two events are going to be dependent on each other. Okay, now, this looks a tiny bit different than any of the ways we've written probabilities, just a little symbol that's in here. But the way you write this, probability, I'm just going to use the P for that, and then in parentheses, it'll say B, and then there'll be like a vertical line, and then it'll say A. The way you would read that would be the probability of B given A. So that's a conditional probability. The condition is that A already happened. I know A has happened. Now, I'm going to give you a formula for this. And you can use the formula for these problems we're going to look at with the table. But I would tell you it's a little bit easier if you have a contingency table. You don't have to really use the formula. You can kind of figure it out. But I'm going to write it down for you right here. So probability of B given A. It's the probability of A and B. If you guys remember from yesterday, and probabilities get multiplied together and then divided by the probability of A. Okay, now forgive. I'm just going to real quick, because otherwise I'm going to have a problem with this on the screen. I'm going to rewrite these numbers that are in the table at the top just so I can show it to you guys at the same time without making it unreadable here. So here was the table just from the top. So this is right-handed, left-handed, this is male, this is female, and these are just the totals here. Okay, now find the probability that says the person is right-handed given that they are female. Okay, so given that they are female, whatever the condition is, given that they're female, that's what you want to put on the bottom of your fraction. So there are 48, remember these are the data here, and then the other ones are really just the totals. There are 48 females. Okay, so what is the probability now? Given that I randomly drew somebody out of this table, I know it's a girl, what is the probability they're right-handed? What would you put on the top of the fraction? The 44. All right, so it's just a little bit different. Now these, I'm going to grab my calculator because it's not over 100, so I'm not exactly sure what these decimals are. So this is about, I'm going to go 3 decimal places, 0.917. So just a little bit lower than 92% would be your probability here. Okay, so the second one says, let's find the probability the person is female given that they're right-handed. So if I'm looking at this, given that they're right-handed, the number of right-handed people, I'm assuming that's what's happened here, there's 87 right-handed people. So that should go on the bottom of the fraction. That's the probability of the condition. That goes on the bottom. What would you put on the top of the fraction if I'm trying to figure out the probability of female given that they're right-handed? Given that they're right-handed, the 44. I know this tree, it's actually 44 for both of these on the top. They are different in terms of their probability, but given, basically I would only look at this column, because given that they're right-handed means I picked somebody out of this column. So it's the 44. So to do that real quick, 44 over 87, this is about just a little bit less than 51%. I'm just going to go 3 decimal places, about 0.506. Okay, what is the probability I pick someone that's left-handed given that I picked somebody that was male? So in that case, what I would tell you, I picked somebody that was male. So there's 52 people. So I would only look, I know I had to pick a guy. So what's the probability they'd be left-handed? You put the 9 on the top. All right, so you're only going to look at one column or one row when you're doing a conditional probability. This is about 0.173, so like 17.3%. Okay, and then the last one says the probability they're male given that they're right-handed. Okay, so given that they're right-handed, I'm just going to cover up the rest of that. That right-handed column, you got 87 people. Probability that they're male, if I know that they're right-handed, I'd put that 43 on the top. So this is just going to be a little tiny bit smaller than the one right above it. This is, what did I just do? 0.494. Is anybody having a question about calculating that from a contingency table? It's also called a frequency table if you see that terminology. Okay, now you don't have to do anything at the top. This is another way though that you can kind of visually display a probability. It's called a tree diagram. So I just kind of stole these lovely pictures from the internet. So just to illustrate what a tree diagram looks like, this illustrates flipping a coin, what a tree diagram would look like from flipping a coin. So I'm going to start here, and if I just flip a coin, there's 2 possible things that can happen. I can get heads, which you see at the end of that little arrow, or I could get tails, which you see at the end of that arrow. So those little arrows are called branches. And this is just like the very beginning. You could make this really elaborate and huge and take a big piece of paper to do, you know, multiple different things that could happen. If you would toss the coin like 10 times, I could make a huge tree diagram for that. This is just one toss. So the way this works is once you start, the probability of that event happening is written along the branch, and the event or the outcome is written at the end of it. So this is just saying it'd be a 50% chance I flip heads, 50% chance that I flip tails. That's the beginning. The little arrows, like I said, they're called branches. All right, now the second thing is just a little bit like a next step to the same tree diagram. So it's very same thing. Flip a coin, heads or tails. Probability is 1/2 for each. And then the second part of this tree diagram, so this is another set, the branch here and the branch here would represent I flipped heads. Now what is my possibility for the second flip? Still heads or tails, and still the two branches that go into the same piece, they should always add up to 1. So a half and a half, a half and a half here. So the two branches together that go to the same point, they add up to 1. All right, so this is heads, 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 tails. This one's tails, heads, tails, tails. And the way you calculate the probability is you multiply just along the arrows. So if I wanted to calculate, for example, the probability, I flipped heads twice, I would take 0.5 times 0.5, and that would be illustrated right there. They show you a bunch of probabilities for the whole table here. But if you want to say, what's the probability I flip heads twice? You just multiply the two probabilities along those branches. That'd give you 0.25. If you have all the outcomes probabilities calculated, if you add down those numbers, it should always add up to 1, would be the probability. So we're going to draw a little tree diagram for a situation underneath here. Okay, so this says, school system compiled the following information from a survey it sent to people who were juniors 10 years ago. Okay, now it says 85% of the people graduated from high school. So that's what I'm gonna start my tree with. So I'm just gonna draw a little arrow, and at the end of the arrow, I'm gonna say they graduated or they didn't graduate. And feel free to abbreviate. You don't have to write about a novel or anything like that. Okay, so it says 85% of the people graduated. So I write the probability along the branch that goes towards that outcome. What would I write along the other branch for people that didn't graduate? 15, right? Okay, so they just have to add up to 1. So this is just going to be 0.15. They don't outwardly tell us that in the directions, but that's what we would write. Okay, now it says of the students who graduated, so I'd be working on that top branch, it says 90% are happy with their present job. So from the graduated, I'm just going to make 2 more branches here. So this would be happy with their job, not happy with their job. So it says 90%, so I'm going to write 0.9, are happy with their job. What would you write on the branch for not happy? 0.1, right? Okay, 90 and 10 add up to 100, so that would be it. Then the next bullet point says of the students who didn't graduate, so that's the other branch coming off the first part we made there. Let's see, 60% are happy with their current job. So from here, happy with their job, and then not happy with their job. 60% are happy, so I'm going to put a 0.6. What would you put on the branch for the people that aren't happy with their job? 0.4. It has to add up to 1. The 2 branches that go to the same vertex, if you will, they have to add up to 1. Okay, so there's our beautiful tree diagram. Now, underneath here, it just asks us to calculate a couple probabilities here. So this says, what's the probability? And these are not conditional. I'm gonna actually, to the side here in a second, I'm gonna make up a conditional probability just so we can practice it here. But for this one, it's just, we're gonna multiply straight across the branches here. What's the probability that a person in this group graduated from high school and they're happy with their current job? How would you figure that out? They graduated and they're happy. What's the probability of that? And if you remember, and means we're going to multiply. How would I calculate the probability I grab somebody out of this group? They graduated and they're happy with their job. What would you multiply together? Exactly. You just go along these branches, 0.85, 0.9, that's it. So 0.85 times 0.9, which is going to be, that's not a nice decimal, hang on a second, 0.765. So about 76.5%. Okay, how would you calculate, so that's the one I did with this one here. Grab a different color. How would you calculate, let's see, they didn't graduate and they are happy with their current job. How would you calculate didn't graduate but they're happy with their current job? Perfect. Okay, so didn't graduate would be the 0.15, and then they are happy with the job, the 0.6. So we're just going to multiply those two guys together. And remember, it can't ever be over 1. This one is 0.09, so then that would be 9%. This one right above would be 76.5%. Okay, now I know this is not on here, but there's one like this on the assignment, so I wanted to make one up. Okay, let's do a conditional probability. And before I do that, let me remind you guys of the formula from the front, because I am going to use that here. So the formula from the front was the probability of B given A can be calculated, probability A and B. We just calculated that for a couple things, divided by the probability of A. So that was from the front. I didn't use it with the contingency tables because sometimes it's easier to just figure those guys out from the table. Now, I'm just going to make up a problem. Let's say I did probability the person is happy given that they happy with their job, given that they graduated. Okay, so this is a little bit different calculation than that first example underneath the tree diagram. So if I do a conditional probability, the probability of the condition goes on the bottom. So the graduated part, I could automatically just put that 0.85 in the bottom. It's just a little bit different to read it that way from a tree diagram than it is from a contingency table. Now, the probability of A and B, so that would be that I am happy and I graduated. So we actually calculated that in this example underneath here. So the probability that I'm happy and I graduated would be to multiply these two guys together. That would be the and. So this would have that 0.765 just from that example right underneath there on the top. But it's just a little bit different probability if you're calculating a conditional. So this is going to end up being 0.9 or 90%. Is anybody having a question? I'm going to use that formula again for the way the last example is written down here at the bottom. So this is another format that you could see this in. Okay, so it says using the information at the right. So over here I have, it says 39% of people in this survey. Doesn't tell us how many people specifically, it just gives us these percentages. These have 39% have a pet, but it says and have had a pet in the past, okay? It says 61% don't have a pet now, so just don't have a pet now. 86% they have a pet now, and 14% do not have a pet now and have never had a pet. Okay, don't write this on your paper because I just wrote it above there and you maybe just wrote it again, but I'm going to write this formula. It's probability of A and B over probability of A. So these two statements here that have the and in them, we're going to use that in these questions. Okay, it says a randomly chosen respondent to this survey has a pet given that they have had a pet or has had a pet. So I'm going to say probability they have a pet given that they've had a pet. Okay, now if you remember, what goes on the bottom is the probability of the condition. So at some point in the past, this person has had a pet. So has had a pet or have had a pet is 86%. So I'm going to put that 0.86 on the bottom. Okay, probability of A and B. So they have a pet. If I'm looking through here, this one says have a pet now and have had a pet. So this is the A and B just given to you in a percentage format. So you just put the 0.39 on the top. And then we would just divide those to get the percentage. You really don't need the decimal. You could just do 39 divided by 86. It'll give you the same probability. This is about 0.453. So you assume the condition happened. That goes on the bottom of the fraction when you do the probability. And then the probability of A and B goes on the top. All right, so this second example says randomly chosen respondent has never had a pet. So I'm going to write never had pet given that they don't have a pet now. Okay, so on the bottom, we're going to assume they don't have a pet now. So it says 61% don't have a pet now. So 61%, so the 0.61 would go on the bottom, and then have never had a pet. This one, let's see, where's it at? Don't have a pet now and have never had a pet. That's 14%. That goes on the top. And so we would just divide those. This is about, actually to 3 decimal places, I would do 0.23. So this is about 23% probability out of that group. Is anybody having a question about the conditional probability? Okay. Homework today is on